Now we're moving on to 17.3, electrode and cell potentials. Here we're going to describe and relate the definitions of electrode and cell potentials, interpret electrode potentials in terms of relative oxidant and reductant strengths, and calculate cell potentials and predict redox spontaneity using standard electrode potentials. If you're 21 or over, this is practically a drinking game of how many times can I say potential in this one section. All right, so let's talk about these. When we have a circuit, which we create with the galvanic cell, we have a flow of charge, and this is the result of an electrical potential difference between 2 points in the circuit. So this electrical potential is the ability of an electric field to do work on charge. So in a galvanic cell, this is called the cell potential. So the flow of charge in a galvanic cell results from the difference in electrical potentials at each electrode. So one side has a higher potential than the other, and the electrons flow to balance it. This here is called the standard hydrogen electrode, or She. She's pretty cool. And this is a half cell, and we use this as a standard value, and we'll talk more about this a little later, but here's just showing you another type of electrode. Its half reaction that it's looking at is 2H plus 2 electrons going to hydrogen gas. So again, the driving force of an electrochemical reaction is measured by the standard cell potential, and it depends on the nature of the redox reaction and on the concentration of the species involved. We do have standard potentials, so we've been talking about all these standard values, Gibbs free energy, enthalpy, entropy, all that stuff, and we have standard cell potential as well, which we use with this E naught. And these are measured when you have aqueous concentrations at 1 molar, the gas pressures, any gases are at a pressure of 1 atm, constant temperature, generally at 25 degrees Celsius. And then the units that we use for cell potential is either volts or millivolts. So make sure you're paying attention. You might be given something in millivolts and you need to change it over to volts to do calculations. So the overall cell potential is equal to the potential of the cathode minus the potential of the anode, which makes sense, right? Because it's kind of like saying final minus initial. So it's kind of like a change in potential. And then, like we already know, any redox reaction can be split into 2 half reactions. So we can look at those half reactions and then the potential for each one. So for instance, this half reaction of zinc solid going to zinc 2 plus has a standard potential of positive 0.762 volts. So let's go ahead and look at an example where we want to calculate the standard potential of this galvanic cell that I copied and pasted the picture since it was talking about figure 17.3. Oops, sorry, didn't mean to push that. So this is a galvanic cell, and so we have the anode, which has the copper, and the cathode, which has silver. The cell reaction that's happening is you have solid copper and 2 silvers becoming Cu2 plus and 2 solid silvers. So then you look up in your appendix, so appendix L, I believe it is, or in your book, table 17.1 has some values, not necessarily all of them, so your appendix is going to have more values. So your anode half reaction is your copper going to Cu2 plus, aqueous plus 2E minus, and the standard potential of this copper is equal, so it has an E naught equal to 0.34 volts. Oops. I cannot write today. 0.34 volts. And then the cathode is where we have 2Ag plus 2 electrons going to 2Ag solid. And its standard potential is equal to 0.7996 volts. So then the potential of this cell is equal to potential of the cathode minus that of the anode. So this is equal to 0.7996 minus 0.34. And so this is equal to positive 0.46 volts. So this is a spontaneous reaction. We know it is because when you just have it all in one cell instead of having the half reaction separated, you see the reaction happening. And it still happens when you have it set up as the galvanic cell. So I want you to keep in mind that this is a spontaneous reaction and that the sign of the potential for the cell is positive. So we'll revisit that, but just keep that in the back of your heads. Okay, so let's talk a little bit more about measuring these standard potentials. We can't measure the potential for just a half reaction. We can only measure the potential for a cell because it's the whole redox reaction being measured. I can't take my voltmeter and just stick it in half of the cell and get a potential. It measures it for the whole reaction. So there has to be some standard reduction potential that is set. And that is using the She cell. She sells seashells? Sorry, I couldn't resist. It's like pretty much every chemistry professor is going to do that when they introduce the She cell. So this is for the reduction of two hydrogen ions to hydrogen gas, and it's been assigned a value of 0 volts. Not necessarily that it is 0 volts, but it's what we use as our standard. So that is then measured against the different different half reactions, and that's where we get their standard potential from. So that is this cell here. So this is the standard hydrogen electrode, the She cell. So then the potential of a cell is equal to that of the cathode minus the anode. So the She cell, in this case with zinc, was used as the cathode, the She cell was used as the cathode. The zinc then was our anode, and so then we get an overall energy of the cell by doing this. So that's where that 0.762 volts comes from. This is also showing measuring the potential for copper. So this is copper then against the She cell, and then you use that voltmeter to get your electron flow. And you can just put the hydrogen electrode on whatever side necessary to get a measurement. So if electrons aren't flowing, then that means your potential is opposite, so it's not a spontaneous. So you can just go ahead and switch it, and then when you do that, you switch the sign of your volts. So table 17.1 gives you some selected standard reduction potentials. And again, these are reduction potentials is what we're looking at here. But your appendix has many, many more values for this. Okay, so like I talked about already, a spontaneous galvanic process has positive cell potentials. If it's non-spontaneous, it's going to have a negative potential. So if you have a stronger oxidant, these are the ones that are going to have a greater standard electrode potential. So when you have the potential of your cathode greater than that of your anode, you're going to have a spontaneous process. So then if you remember from when we've talked about spontaneous versus non-spontaneous, the reverse reaction is then going to be non-spontaneous so if your forward reaction is spontaneous, the reverse is non-spontaneous, and vice versa. If your forward reaction is non-spontaneous, your reverse is going to be spontaneous. So we can use this to predict redox spontaneity. So we're told we want to know if aqueous iron 2 ions are predicted to spontaneously oxidize elemental chromium under standard state conditions. And then we're assuming half reactions are those available in table 17.1, which greatly reduces the potential reactions to look at. Instead of going through the appendix going, oh my god, there's all these different iron 2 chromium reactions. In this case, it's saying, hey, stick with the table, you're good. So we have, when we look at the table, the reaction should be this solid chromium with iron 2 plus becoming chromium 3 plus and solid iron. Because we're oxidizing chromium, so that means it needs to go up in oxidation number. So in this reaction, it's going from an oxidation number of 0 to an oxidation number of positive 3. So if all you want to know is yes versus no, you can go ahead and look at your values. Since iron is the reductant, iron is the oxidant, chromium is the reductant. Iron is above chromium. And so since it is going to be at the cathode, it has, where was it? Yeah. So it has a higher potential than your anode, which is chromium. And because it's higher, cathode is higher than anode, it's going to be spontaneous. But if you want to look at the numbers, the potential for your cell is equal to the potential for the cathode minus the potential for your anode. And so for the iron half reaction, when you look that up, it's equal to negative 0.447 volts minus the anode potential for the chromium, and that is equal to negative 0.774 volts. So then together this is positive 0.297 volts. So yes, this is a spontaneous process. Okay,